So guys, sorry for the technical delay. Command F1 saved the day, so thank you very much. And I have a lot of experience in these matters, so all good. So let's start. Imagine this, a system built for quick development and innovation struggles to keep up with its own success. At Wix, we created small-scope microservices that are automatically scaffolded with single-entity specific domain events. So that has enabled us to really drive our growth and empower developers, but it also brought a few challenges. Performance issues, cost, and also complexity has soared. So the question in front of us today is, can you scale to thousands of microservices without sky-high costs or slowing developers down? So this is the challenge that I'm going to tackle in this session. So welcome everyone, Dzień dobry. Thank you for joining us. And today I'm going to take you on a journey of how Wix scaled to thousands of microservices, the challenges that we faced, and how we reimagined our architecture to blend microservice flexibility with monolith efficiency. So by the end of this talk, you will gain insights into how we tackled the challenges of high-scale systems, the strategies to improve high scale and performance, and the lessons that we learned for merging these architectures of microservices and monoliths. My name is Natan Silnitsky, and I'm a backend infrastructure tech lead at Wix. And for the last 8 years, I've been working on all types of tools and frameworks around the backend infrastructure, including CI/CD, many years in Kafka area, and in the last 2 years around microservices frameworks. I've given a lot of talks in numerous tech conferences around the world and wrote a lot of blog posts on these topic matters I mentioned. And other than that, I'm also a big yoga and fitness enthusiast. Helps you keep calm, yoga. For those of you who don't know, Wix is a powerful website building platform for any type of user, from the grandmother to the professional designer. And we were pioneers of using AI already 10 years ago, so millions of users have created their website in just a couple of minutes. But Wix is not only about a website platform, it's also a powerful business platform with many different tools, from managing your bookings and schedule for your yoga Pilates studio to sophisticated e-commerce tools like dropshipping with third parties. Our aim is to empower any size business, tiny to huge, to utilize the powers of the Wix platform, which means that we need to handle very large scale and also a lot of various different business use cases, so we have a lot of challenges. Specifically, with the Wix backend, we process around 5 billion daily HTTP transactions. Our tech stack is mostly JVM, Java Scala, but there is also a Node.js. But that's the tech stack. In order to handle all this scale around the world, to be responsive, we have 6 data centers spread out globally within 3 regions. So the Wix backend infrastructure mission is to enable creation of extensible backend services for thousands of developers at scale. And it's not only internal developers at Wix, it's also for external developers who write apps on the Wix platform and other types of external development. So in order to empower these services creation to be fast and quick and efficient, we created the Nile backend platform that allows to focus on small scope microservices, actually single entity microservices. So when you come to develop a specific app, you don't need to worry about the entire business. You can just drill down to a specific domain and work on it. So for instance, for our e-commerce solution, instead of a few monoliths, it was split up to many, many different microservices, so it could speed up the specific development and also allow for extensibility. So external developers can replace whatever they want from this list and plug in their own logic, but still have everything usable. So this backend platform really accelerated development inside Wix. We provided auto-generated boilerplate, so a lot of different concerns were already done, technical concerns, including GDPR compliance and a lot of other things. Basically, the developer gets a suite of tools with only a minimal configuration to set up, and they can focus on the business logic of the inventory service. But that meant that we exploded in the usage of this backend creating platform with close to 4,000 backend services, most of them written on the Nile platform. And surprisingly, a lot of these services actually don't get that much traffic. So we start off with, in our backend funnel, with traffic coming to the API gateway with millions of requests per minute. But when you drill down further down towards the e-commerce services, we go from tens of thousands to thousands to hundreds of requests per minute for the more niche aspects of requesting a refund or buying a gift card and stuff like that. So it's important to remember a lot of these services don't get high traffic. And this is how it will appear on a graph. So you'll see that most of services get low traffic and only a small percentage get this huge amount of Wix scale traffic. We have this long tail of services, but a lot of them can still consume a lot of resources, CPU, memory. They take up a big cost. Why is that? Well, the first thing is we work with the JVM stack, and a lot of the frameworks that I mentioned in the beginning with the cross-cutting concerns. So it takes more footprint than in other tech stacks, and you cannot really help it, even if you don't carry any traffic at all. In addition, we want our services to be highly available, right? If one pod goes down, we want another pod to service the traffic. So that means that in each data center, we'll have at least 2 pods. Now, Wix is spread out globally, and we have employed an active-passive DC architecture. Means that we have a passive DC on standby mode, waiting to get traffic if needed. So that means we actually have between 4 and 6 pods at minimum for each of these small microservices, even if they are on standby and doing nothing. So all of that means we get a higher bill with our cloud providers. So that's something that in the long run is not really sustainable and has to be addressed. Other than that, there are more scaling challenges here. First, you want to update urgent security fixes throughout your microservices. For instance, the log4j infamous zero-day attack where everyone had to upgrade the log4j library. So it takes time to deploy all the 4,000 microservices with that, even with a lot of them getting automatic scheduled deployments. Still, you need to chase sometimes service owners to get that happening. In addition, you get increased network latency. Why? Well, we have more microservices involved in the same business flow. We get more hops between them. That will increase latency. Other than that, like I mentioned, we have mostly JVM, but also a Node.js stack. And they continuously had to catch up with the features that are present for fast developing quickly the JVM service. So that's also unsustainable to have so much infrastructure built in multiple different tech stacks. So the core dilemma here is how to sustain flexibility with the developer experience, moving quickly, especially in today's world when you have to move quickly, versus being more efficient and cost-effective. So how can do we need to drop maybe microservices and go back to monoliths because they are more efficient? I mean, that would be more cost-efficient, but it will definitely hurt the developer experience, right? So we decided not to give up, and thus the Single-Runtime project was born, and its vision is to develop like a microservice, but run like a monolith. So this may sound to you like some phrase that an AI made up, where you get the prompt, please sound like Muhammad Ali. But actually, it's a direct quote from Wix's head of engineering, Aviram Mordo, that wants us to think outside the box. So the idea here is that developers keep developing their own niche microservice in their team, but somehow bunch everything together like a virtual monolith and run it together. So, and in order to solve all the challenges that we face. So the team in charge set out to work. So how do you realize this single runtime vision? Well, if we take a closer look at the backend platform Nile for developing a backend service, you see that a lot of the code is actually of these frameworks, of these cross-cutting concerns, and only a small portion will be the actual business logic code. It's actually more than 90%. It includes a data layer, a very complex document-based database that really solves a lot of the issues for developers, including GDPR concerns and a lot of different other concerns. You need the RPC server. You need to support Kafka and publish, subscribe, and a lot of other asynchronous programming on top of that. API validations, user context propagation, feature toggles, A/B tests, and a lot of different other concerns. All of that really puts a massive chunk of repeated code in each of these Nile services. So we definitely want to split up the business logic from the frameworks, and the code already enables doing that relatively easy because there are different developers working on these different parts, and the application developer just focuses on the business logic part. And then we can actually reuse these frameworks, right? And not have them duplicate again and again in each of the Nile service instances. So we want then to have like a more server-client kind of relationship where the client side will be these guests, the business logic, and the server will be the host. And this host needs to enable all of these guests to work. So it has to be multi-tenant in order to get all these guests going. So here we kind of came back to a virtual e-commerce monolith here, right? Because we have all of our modules in the same place, orders, carts, inventory, but basically this is still a microservice. It just has its business logic. So the idea to bundle all of the e-commerce services together is to get them more closely, physically deployed together, which will mean that you'll get less external network calls, and hopefully this locality principle will mean faster performance, lower latency. So with this virtual monolith idea, we want to achieve the goals of cost reduction because we don't duplicate the framework code anymore, better performance with the locality principle here, and we'll get infra upgrades much easier because you only need to update the frameworks part, and that will be controlled by a small part of the organization. It's not spread out the entire organization. Okay, so we want to move to this host-guest architecture. How do we achieve that? How do we create this single runtime solution? So what are our requirements? We need to have guest isolation, meaning that these guests cannot be interfering one another in terms of their memory and CPU. That will be bad. We also want to have fast host-guest communication, right? We don't want this solution to have too much overhead and make our performance unsustainable. We want the guest footprint to be as small as possible to reduce costs. And let's not forget that we still want to have safe production changes, right? We want to have a control of gradual rollout process both for the guests and the hosts, in order to make sure that we don't break production. So our first attempt was to look at GraalVM. So for those of you who don't know, GraalVM is a virtual machine that supports running different kind of languages, a lot of them, and it also has the ability to run them, be multi-tenant, right? So you can actually deploy multiple applications on the same GraalVM instance. It also has the native image that allows to have more efficient footprint and stuff like that. So the multi-tenancy foundation for GraalVM is called isolates. And these isolates create just an execution context that is separate from the process. So each of these execution contexts actually share the static code, but they have completely separate heaps, meaning that like the Java object references won't be tangled between them. So there is this isolation level, and it also offers us good security so that we know that you cannot inject code between them. So we can probably run the host and the guests as isolates inside a single GraalVM instance and gain the benefit of this isolation in memory. But it turns out that GraalVM doesn't provide an isolation on the CPU level. So if one of these isolates starts hogging the CPU because of some spike, then the other guests will be starved of CPU, and we cannot have that. In addition, GraalVM doesn't get you support for deployments, gradual safe deployments, or auto-scaling, which means that all of that will need to be created from scratch, so we won't be able to utilize Kubernetes, for instance, for it, because we are based on GraalVM. So we decided not to continue with this idea, and instead turned our eyes to Kubernetes. Now, in Kubernetes, we have this regular deployments where the pods are part of a replica set, and you can gradually deploy new copies of the pod all around the Kubernetes cluster in different Kubernetes nodes. In addition, and very importantly, Kubernetes offers us the daemon set. Here, pods that are part of the daemon set will be deployed with just a single copy in each of the Kubernetes nodes. So all Kubernetes nodes will get a single copy of this pod that is part of the daemon set. And a very popular use case for this is to scrape all the logs from this Kubernetes node or Kubernetes machine. So we can actually take the regular replica set pods and deploy a guest through that. And we can use the daemon set to have the host deployed in this fashion. Now, we can still get a relatively small footprint for the guests, as we can try and minimize the image of this pod as much as possible. We already removed all the framework code from it. And if we look at the basic architecture here, so we have the daemon set pod, the host. Here we have all the different cross-cutting concerns I mentioned, data layer, Kafka, user context, A/B tests, etc. But the guest only has a tiny guest framework interop, which interrupts with the host. Now, because the guest and the host are on different pods, they cannot, we cannot currently do this easily with in-memory communication. So we decided to still use the gRPC that we utilize between regular microservices. But we saw that localhost gRPC really doesn't have almost any overhead. It's like a few microseconds. It's really negligible. So, and gRPC is very good for having a proper protocol as well, based on protobuf. So we went with gRPC. And then the final point is here is that the pod cannot access anything from the external world without using the host. So the host is the sole proxy for the pod. So this means we get better security because no one can directly access the guest not via the host. And if we zoom out a bit, we see that the guests cannot interact with one another only through the host, and also if they want to access other Wix services outside of these setup, the database, everything will be done via the host. Now, we have moved to a client-server architecture inside a single logical domain, right? So we actually need to make sure that this host-guest relationship keeps backward compatibility. So the host needs to be able to communicate correctly with both today's deployed guests, but also guests that haven't been deployed for a month. So because we utilize gRPC and protobuf, we can get most of the backward compatibility out of the box, as long as we don't completely delete existing fields. But we also need to handle forward compatibility, which means that we have today's guest and it's interacting with today's host, but if there was an important change in today's guest and the host for some reason was rolled back to be yesterday's host, then this guest still needs to communicate with yesterday's host. So as long as you first deploy the protocol changes and only then employ the logic in a gradual, safe manner, then you'll be all right. But you can see here that a new concern has arisen with like a more gradual, safe change that didn't happen before it when it was just a regular standalone service. Now, in terms of gradual rollout, we're coming back to Kubernetes. How will we achieve that? Well, for guests, it's the regular replica set, regular deployment. We just deploy the guests throughout the Kubernetes cluster. But what about the daemon set? Well, with the daemon set, it's more tricky. It's a more important point in the system. And what can you do with Kubernetes deployments of daemon set pods? Well, you can specify how to deploy them one by one or even faster, but over the entire Kubernetes cluster. Well, that's a bit too much for such an important piece, critical piece of the architecture, to just quickly deploy it all around the cluster, because that's not safe enough. So we decided to have a custom solution here, a custom tool. We actually rename the same host code base to different names. So we have a host canary. And this will be deployed in the canary node group, so not on the entire cluster, and can be tested out. And when we feel safer about it, we can start deploying more node groups, so host 1, host 2, host 3 conceptually. So Kubernetes doesn't understand that it's actually different, that it's actually the same code base. It thinks it's completely different artifacts. And this way we can control the level of parallelism. So we can do a lot of node groups at the same time or not. And we control the rate and control the amount of safety versus velocity for gradual deployments of a host. Okay, so we seem to be quite there with our Kubernetes-based approach for our single-runtime solution. We have guest isolation. These guests are just Docker containers, so definitely guaranteed isolation there. We have fast host-guest communication. Basically, we noticed the communication between the host and the guest is up to 2 milliseconds. So it may sound a lot to some of you, but remember that services need to interact with the database, they need to interact with other services to eventually get the response out into the internet. So it will take 10 milliseconds, even more. So this 2 millisecond is a good trade-off in our case with what we want to achieve. The guest footprint is smaller, there's no frameworks there, and we keep working on making sure to keep it as small as possible. And we also solved gradual rollout, some of it with Kubernetes out of the box, some of it with the help of an additional external tool. So what were the numbers of this design. Did it work? Well, actually, surprisingly, yes. We were able to reduce CPU usage by 27% from 30 standalone, comparing 30 standalone Nile services with a host plus 30 guests in a single runtime. And also the memory, we're able to reduce by 32%, actually. And more importantly, I remind you of the long tail of traffic with a lot of our services, that some of them get low traffic, some of them are just sitting idly by. So we can really squeeze a lot more guests into a single Kubernetes node than with our regular standard applications. So actually 4 Kubernetes nodes were able to fit 30 Nile pods, while it only takes 2 Kubernetes nodes to fit a host and 30 guests on average. So that's a 50% improvement, reduction in the number of Kubernetes nodes. And more specific benchmark results for some key resources. So real memory, we have a very big JVM solution for our microservices. With traffic, it gets to 1.8 gigabytes on average. So with our Single-Runtime solution, we were able to drop the guest to take only 900 megabytes. If you amortize the memory cost with the host as well, it's 1.2 gigabytes. In terms of active threads, also a big drop from 150 to 90. And that's also important. We don't, so we reduced heap, we reduced a lot of other memory, and we don't want to have all these additional stack traces as well. So what did we gain with realizing the single runtime vision? First of all, we got a really smooth migration. How come? Well, our backend platform, Nile, was already dedicated to having developers focus on the business logic. So everything, the change to client-server architecture behind the scenes didn't affect them, and we can do it behind the scenes in a very smooth manner. So we're glad about that. I showed you the substantial resource usage decrease with 50% reduction in Kubernetes nodes. And we gained the faster deployment of framework upgrades because you don't need to make sure all the 4,000 guests are deployed. You just need to make sure the host flavors are deployed, and that's something that infrastructure controls. What did we sacrifice? So we had to introduce this extra client server between the host and the guest for the services communication, which added the overhead I mentioned, and the additional infrastructure maintenance and complexity. We needed to consider the gradual rollouts, how to make sure we have backward and forward compatibility, so it's more complexity, more maintenance. The hosts need to be maintained more by the infrastructure team than it was before. But on the trade-off side, I think it's worthwhile. So what comes next? We want to implement this guest affinity I talked about, so having all e-commerce services put together in the same Kubernetes nodes in order to gain the locality principle of having faster communication between them, not utilizing Envoy or other RPC routers. We want to continue working on performance and resource improvements. It's actually a continuous job that we need to do all the time, but now we can focus a lot on the host and optimize where we can there. And because we have these thin guests, then now we can introduce guests with more languages, because there's a lot less concerns to re-implement in different languages. So for instance, we want to do Node.js as well. So what are the lessons that we learned? First, growth shatters existing solutions. A solution that's correct for 100 services will probably not work when you get to 4,000 services. The right tool will trump a new technology. So we have the true and tested Kubernetes solution for our automatic deployments and for auto-scaling, etc. So jumping that ship towards the shiny Graal VM didn't make sense for us. And inertia costs more than the actual service. So we're in a fast-paced world, a lot of changes. If we just keep doing what we always did, it will end up costing us a lot more. So change sometimes is valuable. So, in conclusion, I showed you the journey from isolation to efficiency. Single-Runtime project actually bridged these competing paradigms of microservices and monoliths in a way that serves Wix scale. And this scale sometimes demands architectural courage. So hopefully I gave you a bit of insight when you need to decide about how to work on your architecture when scale demands it, then you may get the encouragement to do that as well. Of course, I don't recommend to do premature optimizations when you start off. It's just when Wix hit this wall that we needed to do it. So thank you very much. If there are any questions, I'll go to Slido. Okay, so first question, would host daemonset be a bottleneck or a single point of failure in a model? How to manage the risk here? So yeah, that's a good point. Indeed, the host does add another failure point. So we have extensive integration tests at Wix for all of our infrastructure, where we try and get as close to production as possible. Now, because we have this high availability principle, we make sure that guests are not, there are at least 2 guests of each service, right? And so they are deployed with anti-affinity in Kubernetes, for those of you who know, which means that you can make sure that these guests won't be deployed on the same Kubernetes node. So that reduces the risk. And also the gradual deployment I talked about earlier is crucial here. It's changes in the host as it covers the entire Wix system have to be done slower and more carefully. But at the end of the day, it's worth it when you want to achieve the goals that we wanted to achieve. Have you considered OSGI as a solution for sharing JVM host code libraries and saving memory CPU? I'm not aware of this tool or framework. And there are also other ways to perform network calls between a host and a guest. Currently, we think Kubernetes is the right trade-off for us. But I'll try and look this up and see, but we haven't checked it out yet. There's also the question of the organizational experience and know-how, especially in larger organizations like Wix. So if you can change your existing application layer, but keep the system relatively intact and not do major changes like in the cloud infrastructure, then it will probably be a better solution for the organization. But I will never say to not explore other opportunities if they can give us a lot of benefits. Okay, what do you mean as frameworks? My first thought was Spring, Hibernate, etc., but you couldn't extract dependency injection out of the guest code, right? So actually, we don't have like implicit dependency injection in our system with the annotations. We have a lot of code generation in our frameworks. Basically, the Nile service generates a lot of these different internal frameworks. It's not like out-of-the-box frameworks. It's a lot of code that infrastructure teams for the backend have implemented. and it's, like I said, it's code-generated. There are dependencies between them, but all of that is abstracted away. What the application developer sees is just the ability to add modules and remove modules and to configure them if they don't like the defaults. And then they can access them in the context of their RPC service and their Kafka handlers and stuff like that. All of this glue is done with a lot of code generation behind the scenes, basically. Any thought on optimizing the small guest GraalVM native images, Java or Crack or other optimization? So native image is a great way to reduce costs. Fortunately, Wix has thousands and thousands and thousands of third-party libraries in use. So it's quite hard to find versions for all of them that support the native image. That would be lovely. I think we definitely going to explore all kinds of further optimizations, focusing on the host side mostly, because that's where the biggest chunk of the cost remains. And yeah, we keep our minds open for that. Okay. What exactly is a guest? What is the difference with how you used to run your service? So in terms of when you develop your application, you mostly see the RPC service. It's also exposed as HTTP, and all your Kafka handlers. All of that is defined in protobuf as you expose your APIs. So in terms of application development, you won't see any difference. It's actually just adding this flag to your service, and the service will automatically be split up to be a guest. So I hope I answered that question. Isn't framework lock-in a serious trade-off here? It seems you no longer can use different frameworks for different use cases as you can with microservices. So maybe I didn't fully understand what are these frameworks. All these frameworks are built in-house by Wix. Of course, we have tons of third-party, and that's always a mess. Like sometimes it takes years to upgrade a major version of a third-party in such a huge code base. So in terms of that, there's not a lot of lock-in. We have a lock-in with protobuf, gRPC, and Netty currently, I would say, and all the generators for the JVM languages. But other than that, I don't think we have a lot of lock-in. We have the infrastructure teams that develop the cross-cutting concerns, and they change that all the time. How long did this migration take, or is it still ongoing? We still haven't reached 100%, so it's still ongoing. I think redesigning the infrastructure to guest host took around 6 months by a small team. Most of the infrastructure teams carried on as usual because it's not so intrusive for most of the different libraries and frameworks. And the migration itself has taken 6 months up to now, and will probably take another 6 months to complete completely. Why not to choose something cloud native for host application? Something like Golang to make host apps as small as possible and run IT with every pod. So definitely there are other tech stacks out there that have a much smaller footprint. But at the end of the day, Wix is a big organization with a lot of important code base that serves hundreds of millions of websites and business back offices. So changing to a completely different tech stack is a monumental task for a larger organization. It could be worth it, but you need to make sure maybe AI will help in the future, help make such transitions easier. But what this project did was take a small team and just carve out the host guest from our existing infrastructure and run it. So we didn't get the best cost reductions and stuff like that. We could have with other tech stacks, but it's always a trade-off, right? Is Wix Tiny Framework open source or proprietary? So we do have thoughts on exposing Nile as an open source. We're still in the process of thinking about it and looking at possible market share here, because at the end of the day, the Nile is really geared towards small-scoped, single-entity microservices, right? Coupons, refund, each thing is in its own service. And such API modeling is really helpful for Wix platform. It's really extensible, really flexible. You can plug in wherever you want as a web agency when you need to change stuff, or for other customers, this flexibility. But for a startup or a mature startup, I'm not convinced that it will be that beneficial to, from the get-go, split your model into so many small shards. Usually with startup, you start monolith, you then grow it out to modulith, and then split out microservice from it. So it's more in line with, I think, organizations with this need of creating a very extensible platform. And maybe there's a market for that. How do you glue business logic code with shared infra code to have it different during development? Is it easy to test, to develop independently? Okay. So like I said, we had a lot of code generation for our services to split between guest and host. What we offer the developers of the guest is an in-memory test suite where you get, it's a bit hard to explain without slides, but I hope most of you know the hexagon architecture, where you have the business logic inside and the ports and adapters for all of the concerns that don't contaminate the business logic with Kafka and RPC and everything else in database. So we actually have in-memory representation of all the different technical adapters. So you get in-memory representation of our data layer, in-memory representation of PubSub with Kafka. So all of that is means that we can run tests extremely quickly. And we get a high level of reliability with these tests. Why? Because the infrastructure part has contract tests to make sure that all this in-memory fake representation answers exactly the same way with the real implementation of all these infrastructure frameworks. So in terms of developing it on the application side, it's much easier. And I think, I hope I answered this. Basically, it's developed completely separately, but we do have these test apps to make sure that everything continues to work as we change the infrastructure. Your gRPC API, how big and complex is that? How is that version, document, etc.? So, like I mentioned, we use protobuf. We have infrastructure that automatically documents it outside the platform. Of course, there are open source tools out there, Swagger, that does this beautifully as well. You don't have to do custom on top of that like we do, but it's important for us to have nicely documented for the Wix platform. Versioning. So there are several strategies. First, your services have exposure, and is it private, is it public, is it internal, and is it mature, is it alpha? And once it's mature and you want to do breaking changes, you're going to change to V2, V3. And hopefully your customers will migrate to that, but you'll need to, in the interim period, maintain both V1 and V2. And it's all, of course, automatically documented with the power of protobuf. Protobuf is a very powerful definition language, both for then getting the code from it and getting the documentation out, and a lot of other benefits. Do you experience any significant delays, latency on your daemon sets used as a sidecar? So a sidecar is usually a container inside the same pod, so I wouldn't term this as a sidecar. So our most heavily trafficked services are not currently part of this architecture, which means that we can have relatively consistent traffic incoming to these hosts. So usually we don't see this huge spikes that disrupt the host and get it out of memory and stuff like that. The overhead between guest-host communication, I told you, is up to 2 milliseconds. And as we get this more and more efficient, maybe we'll consider getting to the really high RPM stuff as well. How do you handle asynchronous communication? So I'm not sure in which respect do you mean asynchronous communication, like our RPC NETI-based, you can say that the client does the handling asynchronously, doesn't block anything. In terms of event-driven, we have a huge amount of event-driven flows in our system where the database is changed automatically, Kafka events are sent out, and a lot of services do reactive style work on that. I hope I started to answer that. How was your original solution structured in Kubernetes? So yeah, basically regular services were deployed each like the Java image with the code layer on top of that, deployed with replica set inside the Kubernetes cluster. Nothing unique or special about our original solution at all. Have you grouped microservices and nodes by communication type through event-driven broker and separately using direct API like RESTful, or had no matter at all? So thankfully, well, a lot of our services are hybrid. They have both RPC and Kafka. And thankfully, we didn't need to stress so much about the Kafka implementation of a host side, because we have an additional layer for Kafka communication with the brokers that we call a consumer proxy. That's a whole different out-of-scope talk where, in order to save costs from the cloud on Kafka, we, on the proxy, consume the messages from Kafka, put them on the local disk, and then dispatch them via RPC to all of the services. Because as the moment you have a lot of consumers of the same topic, it can drastically reduce the amount of Kafka communication, which reduces our cloud bill. So that's another stateless, stateful service that allowed us to be stateless on the host. So the host just redirects the RPC back into the guest. So for the host, RPC is the same for Kafka and HTTP and RPC. What is the solution for guest groups? Is it a custom Kubernetes operator? So we haven't implemented it yet, like bundling the domain-specific groups together, pods together. But I'm sure we will try to use standard Kubernetes solutions. I don't think we use operators that much. We roll our own, I think, stuff. But it will probably be similar to how we deployed the hosts. I think we're out of time. So thank you very much for all your great questions. I appreciate it, and thank you very much again.